Invitation. My name is Fabian. I'm going to talk about ontologies and knowledge bases. I have a few slides about myself to introduce myself. I'm from Télécom ParisTech, as you figured out now. So I'm going to describe my research career so far in terms of three desiderata that I wanted to achieve in my life. I wanted to have money. Yeah, I want to be rich. I want to have freedom. I want to do what I like in life, and I want to have a permanent job. Yeah. So my career started in 2003. I did my bachelor in cognitive science. So that's everything that has to do with cognition, artificial intelligence, and philosophy of mind kind of stuff, neurobiology. My master in computer science also in Germany, and my PhD at the Max Planck Institute in Germany in computer science. And during all these steps, in terms of my desiderata, I was exactly here. Yeah. So I had I had no money, yeah, I had no freedom to do what I wanted, and I didn't have a permanent position. And then I went on and did a postdoc at Microsoft Research in Silicon Valley. And you might have heard of it, you might not, because they recently dissolved. I don't know whether this is because I left or because I was there. I don't know, yeah? So this changed my perspective because now I moved on here. Yeah? Microsoft paid very well. So I didn't have a permanent position. I didn't have the freedom to do what I wanted, but at least I was not poor. I became a postdoc at INRIA-Saclay, so right here a few kilometers from Paris, with Serge Abitboul. And so I moved actually in my goal here. Yeah? So I didn't have money, but I had the freedom to do whatever I wanted. I'm going to show some of the work I did in this talk, and I didn't have a permanent position. Then I moved on to the Max Planck Institute in Germany, in Saarbrücken. I became a research group leader, and I could move on because now for the first time I moved to an intersection here, yeah. So I had money, I had freedom, but I didn't have a permanent position, yeah. And 2 years later, in November 2013, I became an associate professor in maître de conférence here at Télécom ParisTech, and I moved on in this graph. And guess where I moved? Yeah. Here. Yeah. So, yeah. So I have a permanent position. I have the freedom to do whatever I want, but I'm busy writing grants to get the money. Right. So. Apart from this technical career stuff, in my personal life, I'm a big fan of Elvis Presley. I hope you know Elvis Presley. Yeah, yeah. And this is a picture of Elvis in 1961. And this is a picture of Elvis in 2014. Yeah, you see that he became quite a bit older, but you see the smile is still the same. Yeah, so it's still the same smile, and the hair is the same, everything. So we met him recently in New Zealand. Unfortunately, he's not on the picture because we took the picture and we forgot. Yeah. So, but we met him recently, and he retracted from public life. So he's no longer he doesn't give concerts anymore, everything, right? But he still is quite branché. So he still takes a great interest in technological advances and in what happens in computer science and science in general. And he regularly Googles himself, right? Which is one of the things that we maybe do, but he has more results. So he Googles himself, and recently these types of boxes here appear. This is like 2 years ago. These knowledge cards. Yeah. So this has some pictures, and Elvis Presley is a singer and lists some of his songs and so on, right? And Elvis is very interesting, right? Where does this come from, right? So where does this information come? How do they derive it? And in particular, he gets very annoyed because here, yeah, it says like he died in August 1977. Yeah. Imagine how annoying that must be. Yeah. You read your own Google page that says you died. Yeah. Very distinct. So you want to know like where does this come from and how come they are? And so this is a great coincidence because I actually work in this area, and we work on how to construct these knowledge cards, and we work on how we can correct these types of errors. And then I explained to him like what advances we have done in recent research, and this is the talk I'm going to give to you. So these knowledge cards, as you might know, are based on a knowledge base or ontology, which is basically a graph where the nodes are entities such as Elvis Presley and birth dates, so 1935 birth years, and classes such as singer and person and so on. And the relationships are the labels on the edges. Yeah? So Elvis is born 1935, and he's of type singer, and singer is a subclass of person. So those who know this kind of stuff, in everything that follows, we're going to stay with the RDF terminology. We are not going to distinguish the T and A box. For us, it's just a big graph where the top nodes are classes and the bottom nodes are entities and literals. Yeah. Right. So there's a lot of work going on these knowledge bases, and this is the knowledge base life cycle. We're going to start with how we can construct such knowledge bases automatically, derive them from Wikipedia. We're going to talk about mining knowledge in the knowledge bases for horn rules. We're going to talk about aligning knowledge bases, so given two, how can I find what they have in common? We're going to talk about protecting knowledge bases, which is traditionally the most weird and controversial topic in such talks, so I'm looking forward to your questions there. And we're going to talk about a project that we have with Le Monde and Der Spiegel, which is the German newspaper, on applying knowledge bases. So we're going to start here. How do we construct such knowledge bases? So our idea at the time was to start extracting from Wikipedia for several reasons. First, whenever you have anything from Wikipedia, you're automatically right. Yeah? So whenever you have an argument with somebody, yeah, they say like, yeah, the ratio of men to women is like 1.3 in this country or not in this country, right? And some puts out the smartphone, Wikipedia says, bam, you win the argument. Yeah? And we do the same thing. Yeah? So if we extract from Wikipedia, then automatically we will inherit all the authority that Wikipedia gives. And second reason is more technical. Wikipedia pages are very structured, and you can actually go a long way without looking into the text of the pages. Yeah? So already the fact that we have a page means that we can make an entity, Elvis Presley, and because usually Wikipedia entities are disjoint, like unique, means that we're going to have one node for each article, roughly. Yeah? And then we're going to look into the info boxes. We're going to figure out the birth date. We're going to add it here. And the birthplace, we're going to add here. And then we look into the categories. So, for example, he's in the category American singers. So we're going to write here he's an American singer. Yeah. So I think it's not so easy, yeah, if you look at it. And if it were so easy, people would have done it before. It's not. Because like these things here don't map at all to the relationships here in the graph. Yeah. So they sometimes write birthplace, birth date, place of birth, place of death, born place. So they vary quite a lot. So you need to map this to unique relationships here. Same thing here. You can't say Elvis is a rock and roll. Yeah, doesn't make any sense. He's an American singer. He's an Academy Award winner, all right, but he's not a rock and roll. So how do we distinguish the two? And the trick at the time was that we do a noun phrase parsing, and we take the head noun, which is in English it's usually the last noun in the phrase, and it determines the syntactic properties of the noun phrase. And then we look if it's plural. And if it's plural, we put it here as a type. So this is how like rock and roll music, and Elvis music, whatever, doesn't get in there. But like American singers and award winners, this is going to go there. And this is because like only countable nouns can be put to plural. And we put it there, and it works like 95% of the cases. And if something works 95% of the cases, then you just don't touch it. Yeah. This is the technique we applied. We do this with all the pages and link them. So Elvis Presley born Tupelo is the place, we know where it's located, and so on. So it makes it a big thing. And the entire system became quite large. So this is an active project here at Télécom ParisTech and in cooperation with the Max Planck Institute in Germany. And there were like a dozen people working on this. And the entire architecture is now that we have Wikipedia here. We have small extractor modules that extract particular parts. So this guy, for example, extracts only info boxes, and this one looks only at categories. And then we have other sources, and we have again small extractor modules that extract one particular part from this. And then they make intermediate results. And the trick is now that we don't put these results directly into the knowledge base, but we have intermediate more extractors that consolidate the information. They deduplicate, they type check, they check functional constraints. Everybody's born only in one place. They make type coherence checking. So if by any mistake we get like Elvis is a singer, an award winner, and an actor, and he's a guitar, yeah, for some weird reason, we're going to kick out. We know, oh, guitar doesn't fit into this picture. We're going to kick it out. So there are lots of checks actually that follow and that clean out the data, and this is in the end gives this knowledge base which we call YAGO. I'm sure it's going to appear at some point, and this ensures the high quality of 95%. So we did a manual evaluation. We check whether the facts are true with respect to Wikipedia, and we obtain 95%, meaning the data that's in there, we don't have everything, but what we have mostly is correct in this sense. And this we gain from these. I think we can see it locally, this graph, or not. Maybe not. maybe not at all. I think we might have it here. Yeah, so this is the entire graph of extractors as it is in reality. So this is the real thing that's generated from the code, and you see that we have like little extractors, these are the blue dots, and we have intermediate results, and the intermediate results are again used in other extractors and so on. So it's around maybe, by now it might be 100 of these extractors that run in parallel and extract and clean and do all this kind of stuff. Yeah.
I'm sure you're going to talk about this later, but so is this automatically constructed, or is something like a heuristic effort by hand?
So there is the manual part in it is the mapping of the of these attributes to these attributes. We're working on learning that as well, but we can't do it right now. I have a PhD student who will hopefully work on this. And the other part is all automated. So this is a one-time effort. Like we spend like a week mapping these things. We have like 200 mappings. And the rest, like this entire following algorithm is all automatic. It all does it, just runs through. We just regularly run it. Right. So recently, we have worked on extracting from multilingual Wikipedias. So yeah, maybe I can go into detail. Until when? How much time do I have?
1 hour.
1 hour. Okay, then we're fine. Yeah. We have worked on extracting information from multilingual Wikipedia, so from English, from French, German, Italian, Italian as well. Yeah. And maybe I can show how we do this. So the main problem is again these attributes. Yeah. So if it says like was born in the English Wikipedia, it will say est né in the French one, est nato in the Italian one. So how do we map these things? How do we know that this means the same? And so there are different approaches. One is to build a different knowledge base for each language, and this is what our competitor project DBpedia did. Yeah? So they have one knowledge base for everybody, but then you don't really use the synergy between the Wikipedias. Yeah? Another approach is to try to map them among themselves, so to map was born to est né and est nato, but we have different approach. We think that our extractor architecture can actually do the job by itself, as follows. So we extract here by the usual extractors, born in Elvis, USA, Mao, China. I chose these because they're short names, they had to fit into the box. Yeah, there's no political statement that I'm making here. And then we extract just from the French Wikipedia, est né, and we also find Elvis, USA, and Mao, China. So how do we find USA and not the États-Unis? We use Wikidata, which is a big, you might know Wikidata.
China, you did she.
This is what I'm saying. So we can actually translate the entities by help of the Wikidata project. Wikidata is a project that's part of the Wikimedia Foundation, and they want to build up a knowledge base, much like Freebase, by people who type the information manually. So it has very clean information, but not a lot until now. But they are growing. But what they do have are the language links. So they know that États-Unis is USA, and they know that Xin is China. Fantastic. So we use this thing, and so we find that est né has these pairs. And once we found this, we compare these two things, and we do a statistical measure and saying like with which probability does one include the other. And say, look, this has a lot of overlap. I mean, I'm simplifying, right? A lot of overlap is all quantified, a little complicated, but we find a lot of overlap. And once we find this, we say, okay, then maybe est né means born in. Now we can just replace all facts here. Est né we replace by born in, and we gets lots of born in facts also from the French Wikipedia. And then just the remaining steps are always the same. So we disambiguate, we deduplicate, we do type checking, we do constraint checking. So in the end, we just added like 3-4 more extractors to this big scheme that you saw, and it does it for 10 languages, which are the ones that the authors of the paper could speak and validate, yeah, which is Italian and French and English and Spanish, like all the Western ones, plus Arab and Farsi and Polish, which happened to be the languages that we could understand. As it just recently appeared, this paper. And this is an example. So the knowledge base looks like this. You can actually try it out. I'm going to give you the link. This is everything we know about Elvis Presley. And we know he acted in The Flaming Star. He was influenced by this person. He married to Priscilla Presley, and he wrote the music for this Elvis on Tour album and so on. So this is everything we know about him, and we also know where we got it from. Yeah? Some facts we get, most facts we get from English, especially about Elvis. Some facts we get from several languages, here Italian and Spanish. And if you go to entities that are local to a country, for example, French in les chateaux, the castles, then we get the castles mainly from the French Wikipedia, and also the facts from the French Wikipedia, and the German one, who is for some weird reason very strong on French castles. Yeah? So then we get this from there. So this is a huge graph that you can actually try out and use. We combine Wikipedia and WordNet, in case you have heard of these research like WordNet. We have time and space information. We know like when and where stuff happened. We are multilingual, so the browser is already multilingual. We're currently debugging. The data will be online soon. 100 relation, 100 million facts, 10 million entities, 95% accuracy, and our data is used by DBpedia. So DBpedia imports part of our data for their hierarchy. The caveat in this is that our focus is on precision. So we are very aggressive, and whenever something doesn't look right, so for example, like Elvis is a Nobel Prize, Academy Award winner, and he's a singer, and he's an actor, and he's a guitar, we just throw it out. Whenever somebody has 2 birth dates, bam, they both go. We are very aggressive, meaning that we can say we have a cool accuracy, but we are like missing a lot of information that we might get. So this has led to quite a number of publications and a Best Demo Award in this joint work with lots of people who are now at Max Planck, and he's at Hasso Plattner Institute and University of Toronto. And you can try it out, I encourage you. If you get bored during this talk, try it out. Yeah. Right. So what is more? We want to move on and go beyond Wikipedia. And beyond Wikipedia, the first hurdle that we encounter is what we do with named entities that have like similar names or that appear under different names but are the same entity. Yeah? So if you read newspaper articles, for example, like if you read like yesterday a newspaper article about Elvis, for example, yeah, then you will find that he's sometimes called Elvis, sometimes Elvis Presley, sometimes Mr. Presley. It's not clear whether this is the same or not. And this guy is different from the Elvis Hurricane, which is a hurricane. Yeah? It's different. So how do we figure this out? And so the classical way to do this is to use clustering. So we used hierarchical agglomerative clustering, meaning that we build it bottom up. So every mention, like we use a big web corpus, we want to figure out what the words refer to. So Elvis in this document, which Elvis is it? The hurricane, or is it the Elvis Presley, or is it somebody else? So the standard way to do this is to use clustering to work bottom up. And actually, we have to use clustering because we want to deal also with entities that are not in the knowledge base. Yeah? If you have the knowledge base and knows Elvis already, then it's a disambiguation problem. But if you don't know Elvis, then it becomes much harder. Like if you have, for example, the mayor of Paris or the mayor of Saclay is not going to be in YAGO. I'm sorry, it's not going to be there. So the problem is really clustering unknown mentions of unknown entities. And the standard way to do this is by clustering with a number of features. And we use the following. We use TF-IDF token overlap. So this is actually the interesting thing. TF-IDF is this information retrieval measure. Some people nodding? No, I'll say nevertheless. It means basically that we're going to say that 2 entities are similar if they share a component. So for example, Elvis Presley, Mr. Presley, they share the word Presley. But we're going to weight this similarity with the frequency of the word. So Presley is very rare. So we're going to say, look, these 2, they share something very rare. So probably they are the same. While Mr. Obama, Mr. Presley share the word Mr., but Mr. is very frequent, so it doesn't mean as much. So this was this measure. Triple overlap, so we looked it up in a dirty knowledge base, not all knowledge base. String similarity, of course, we used word overlap in the source documents. If I have 2 documents that talk about Elvis and guitars, and I figure out that this Elvis is the singer, then probably this Elvis is also the singer. Type overlap of co-mention, whatever. So now the problem is, if you want to get such a paper into a conference, then you can't get it in like this. You can't simply show something that works. You have to use machine learning. if you want to get the paper into the conference. So, okay, good. We want to get the paper in, so we use machine learning. We use machine learning on all these features. Yeah? And to make really sure that this paper gets in, we also use machine learning just on these features. Yeah? So, look, we have 2 times machine learning, so this paper must get in. And it did. So, we are now in the, it's work at CIKM. We got it in, and the result is basically that this TF-IDF token overlap that I described first works best. It works just slightly worse than all the machine learning stuff. So if ever like you have to match entities, then the TF-IDF token overlap goes actually goes a long way in this thing. And the reason is that that these features are partially very noisy. And if we train machine learning on noisy features, it does not necessarily beat the clean features. So yeah, this has to be taken with a grain of salt always. This is joint work with my student Luis and people from Google and was published last year at CIK. Right, let's go to knowledge mining, which is the project of my student, the most recent one. We want to find patterns in this knowledge base. For example, Elvis married Priscilla, yeah, and Elvis is the father of Lisa Marie Presley, who was later coupled with Michael Jackson, yeah, which is not in this picture, and she is the mother. And so we can mine the rule that if X and Y are married, and X has child Z, then probably Y is also the parent of Z. Yeah? Which doesn't always hold. Yeah, I see faces. Yeah. And actually, in YAGO, it holds to a surprisingly low percentage. And this is because we have in YAGO all the characters from the American soap operas. Yeah? And in these, never ever is the parent the one who is the wife of your. But never. Yeah, but it's like 80%. So all hope is not lost. So we want to mine these patterns. We want to mine them because once we have them, we can use them to predict information. So suppose I know that François Hollande, this is a very bad example. Let's suppose that I know Obama is married to Michelle, and Michelle is the mother of these 2 girls. Masha is probably one girl. Then probably Obama is the father of this girl. Yeah? So if we have such a rule, we can predict information. We can also correct information. If the father of Masha is Elvis, we say, look, maybe something is wrong in your knowledge base. Yeah? We can actually check information. The problem here is that such rule mining needs counterexamples. Because if you just learn from positive examples and you have nothing to correct your rules, you're going to overgeneralize. Yeah? So, for example, there is Woody Allen, yeah, who married his stepdaughter, yeah, under a very weird legal constellation. Yeah? And so, if we have one fact that he married his stepdaughter, right, and you have no counterexamples, you're going to say, oh, people marry their stepdaughters. Yeah? Whereas we have a positive example, no counter information. And the problem in these knowledge bases is they don't contain negative information. So from the fact that Elvis is not married to a stepdaughter in the knowledge base doesn't mean that he is not. It just means we don't know. So there is no negative information here. So there's no contradiction. We can't say, yeah, oh, Elvis married his stepdaughter as well. Because there's nothing that contradicts it, yes.
But you got again the frequency information. So frequent data set mining, one thing that happens only for one.
Exactly.
One item is not.
Exactly.
Not generalized.
Exactly. So we use such statistical measures, support and confidence, and I'm going to talk about the confidence measure right now. So what we did in order to generate first negative examples is what we call the partial completeness assumption. We say that if we know one or several children of Elvis, we're going to assume we know all of them, which is an assumption. So we say, like, if I know that Lisa is the child, then Einstein is not the child. We assume that the knowledge base is complete on this. Whereas if Lisa, we don't know any children, then we're not going to assume anything. She can have children, she can have not, like 10, 15, as she wishes. Yeah, she's completely free in this. Which is an assumption. We have evaluated it manually, and it roughly works. It doesn't hold always. So if you use this assumption, you can generate negative information, and you can find counterexamples, and then you can give a weight to the rules. Plus, we use a very efficient implementation of an in-memory database, which can mine rules on YAGO, on a subset of YAGO, in something like 5 minutes. So it's a very efficient implementation, plus this little trick, plus statistical measures. And this is my favorite rule that we can actually mine. It says, like, if you are a pope, then you will die in Rome. Isn't that cute? We know that the previous pope does his best to evade that fate. He might yet become a counterexample, but until now it's true. So this is a very powerful thing. It can mine such rules on knowledge bases. There is a caveat here. The rules cannot predict the unknown with high precision. So the rules that we mine, the stuff that they predict, does not always correspond to reality. So if we say, like, you should be married to this girl and you should have this child, it's only correct like in 30 to 40% of the cases. So we cannot predict the future. So we cannot say like when a person will die or where the person will die or how many children a person will have. So we can't do that. We are working on that by combining several rules. So if several rules say that you are the father of that child, then the evidence increases and we want to work on that. But this is work in progress. We can't do it yet. If ever we can, then I will let you know. Good. This is joint work with my student Louis, people from Max Planck, and I won the Best Student Paper Award at Good. We move on to aligning knowledge bases. So unfortunately, we are not the only ones who create knowledge bases. I would like it to be this way, but it's not true. So there are like hundreds of projects that create knowledge bases. We're not the only ones. This goes in the direction of what we just discussed. So suppose you have a knowledge base that says that Elvis is a singer, he plays guitar and he was born 1935. And you have another one that says that he's a rock singer, he's married, and he was born 1935, like Elvispedia and YAGO. And now, suppose somebody comes and says, who is the spouse of the guitar player? Then neither knowledge base can answer the question. The left one knows who's the guitar player, and the right one knows whom Elvis is married to, but neither can answer the question. So Elvis is lonely. So we set out to solve this problem of loneliness, and the solution that we came up with is actually a triple matching endeavor, because we want to map not just Elvis and Elvis. We want to find out that rock singer is a subclass of singer, and this is actually asymmetric. So singer and rock singer are two different classes that are not equivalent, but one is a subclass of the other. And the same holds actually for the properties. So if you want to say that born and birthday, they subsume each other, but you can have, for example, to meet somebody and to marry somebody. Not everybody who meets somebody marries that person. Unfortunately, it would be a mess. But on the other hand, like everybody who marries a person meets that person. Fortunately. So previous approaches have tried to solve these problems on their own. So they started like with the instance matching here, and then there's a record linking problem, and then there are other approaches that did the schema matching, the born and birth date stuff. And we thought maybe it would be good to do it all together. So when we know that the two Elvises are the same, this can help us figure out that rock singer and singer are related because they have the same instance. If we know that the two are the same, this can help us figure out that born and birth date is maybe the same. Once we figure that out, this can help us, this can give us more evidence that maybe other people are the same. Then we have other people who are the same, can help us figure out more equivalences between relationships and so on. So it's actually like self-reinforcing loop. I'm going to show that how this works. So here's an example. So Elvis, this is the entity Elvis, is called Elvis. And this Elvis is called Elvis, but with a relationship label. And this is the string, the name, the physical name, and this is the entity, which is an abstract thing. And we start by matching the literals, the strings. This is because in the RDF standard, literals cannot have several denotations. Like a string is always a string. There's nothing that can go wrong. And there are different ways to match these. So you can say, you can have string similarity measures, you can have machine learning in there and everything. And we used a very simple approach. We used the identity function. The identity function says that two strings are equal if they are identical, and otherwise they are not. And this works very well in the experiments we tried. We later broadened this, like we worked also with shingling and string similarities that go beyond simple identity. So we're going to take like trigrams of 3 letters, like Elvis, Elv, Vis, and here the same. We're going to measure the overlap, and this makes it a bit more robust, but it introduced also a lot of noise. So in the experiments we did, like this, the simple function actually works best, but it might depend on the data sources that you're using. Right, we mentioned this. Then we assume that all relations, name and label, are a bit equivalent, like this. But not just name and label, also like label and birth date, birthplace and birth date, everything is a bit equivalent. And now comes the trick. The trick is to match the entities, to match Elvis and Elvis. So you're going to dream of Elvis tonight. Yeah. So they both share the same name. Yeah? And this means a lot that they share the same name. It means a lot more than if they share the same year of birth. Because many people are born the same year, but few have the same name. Yeah? And so we formalize this, we say that the inverse functionality of one object in relation is simply 1 over the number of incoming links. And so this means that for name and Elvis, this is very particular. Few people are called like this. But for born 1935, many people are born there, so this doesn't mean a lot. And then you generalize it, you call it the inverse functionality of the relationship, so of name or of born. And this is just the harmonic mean of the individual inverse relationships. And so that means, for example, that the inverse functionality of name is going to be high because few people share the same name. And the inverse functionality of born is going to be low because many people share the same year of birth. And the nice thing is that if you want to compute this, I think I had this here. Yeah. If you want to compute this, you can actually show that it's the same as the number of subjects divided by the number of facts for that relation. So you don't even have to walk through all objects and count how many incoming links you have. You don't have to do this. You just count how many facts there are, which is stored anyway in your index, and how many subjects you have. You divide the two, and that's it. It's very easy to compute. You don't even need to walk through the facts. And if you now say, we can now use this and say, like, if subjects, these two people, share a relation, yes, they do, name and label, which we assume to be slightly equivalent. And this relation is highly inverse functional, yes, it is. And the object is matched, yes, it is. Then we increase the score here. Puff. We match the two. And then we go on, we say, if relations share many pairs, so this is the pair and this is the pair, we're going to increase this score, and so on. And so then we iterate this process, and then we're going to match, it's going to converge to the case where the good Elvises are matched. Yeah. So there is some caveat here. Yeah. So the model on which this is based is actually a probabilistic model, and these are not the real formulas. Yeah, they're just for illustration purposes here. It says that the probability that two entities are the same depends in a complicated manner on the probability that two relations subsume each other. And the probability that two relations subsume each other depends in a complicated way, it's not the real way, on the probability that two entities are the same. It's a recursive thing that's bootstrapped by the fact that two literals are identical. Yeah? So you bootstrap with the literals and then you iterate. And actually, in all the experiments we did, like we experimented with YAGO, DBpedia, IMDb, and the OAIEA, so this open initiative for ontology evaluation, it always converges, but we can prove convergence only for a subcase. And we're working on this, so we can prove it only a subcase, we don't know. Once we did this, we can now match the classes, and we simply say that two classes, one class subsumes the other if many people here are also here. All American singers are singers, and we just match the two. And this is, again, a complicated formula on which this depends. There is a caveat. The class alignment works only with 85% precision. Yeah? And this is because it is based not at all on the words. So we don't use the fact that the word singer here and the word singer here, they are like similar. We don't use that, or we don't look into it. It's based only on the overlap of instances, which is a very weak signal. And this means that whenever two classes happen to intersect in some way, we say, yes, you are subclasses. So my favorite example is that people from Utah, the US state, is a subclass of murderers. Yeah. Why? Yeah. Because there are 7 people from Utah in Wikipedia, and 6 of them happen to be murderers, and our algorithm makes them all murderers. Yeah. So this is a typical example. Yeah. So this works only 85% precision, but the rest works very well. So the relation alignment works very well, like 95, 97% precision. And the instance matching also works very well. So we call this thing Paris, first because it was constructed in Paris, but then also because it was it is a female name. So all my projects have female names. Yeah, YAGO is a Serbian female name. Paris is a Paris Hilton female name. And also it means like probabilistic alignment of relations, instances, and schema. Yeah. So once we figured out this name, we say, okay, we have to write a paper that does probabilistic alignment of relations in instance schema, and this is what we did, yeah. So this joint work with people from Télécom ParisTech and Serge Abitboul from INRIA Saclay, and we have 2 papers about this. There is a very neat variant of this, which I wanna show, because this thing works great if the knowledge base have the same structure. If I have like born here and birthplace here, it's going to work out. It's not going to work out here. If you have like Elvis is born in USA and the other knowledge base says he is born in city which is located in country, then it's not going to work. It cannot match the 2 things. Yeah? And so here's a solution that we propose. We coalesce the knowledge bases, so we assume the entities have been mapped clock. So meaning that we have only one Elvis and one USA. So we have one knowledge base where every entity appears once, but the edges are like are just merged from the different knowledge bases. And now we use Amy, the rule mining thing. And Amy will find the rule that if you're born in a city and the city is located in a country, like in green, this is from one knowledge base, then we have the fact from the other knowledge base that the person is born in the country. Just run Amy on top of it. We call this a ROSA rule, not just because of female name, but also because it means rule for ontological schema alignment. Okay. And this produces many spurious correlations. So we get lots of rules in the spirit of like murderers from Utah and kind of stuff. We also get, so this is just a huge set, it's just a super set. We don't know how to select the good ones in it. So that's the problem. But there are also very many nice ones. For example, if you're a princess in YAGO, then in Freebase you are a member of the royalty and your gender is female. Yeah? So we can have very complex alignments. Yeah? One class membership becomes attribute plus class membership in the other one, and we can mine these type of rules. Well, but we couldn't get the entire thing done, so we mine way too many rules. We have a superset of the real alignments, which is why it's a workshop paper with my student, my wife, and myself. Yeah. Good. Now comes the controversial part. Oh, are you ready for controversy? Okay. Protecting knowledge bases. Good. We have found out that other knowledge bases use YAGO. Yeah? So DBpedia uses part of YAGO. They just import the stuff. And they are nice. They say, look, this is from YAGO, and they credit us whatever. They are nice. But what happens if somebody else just takes the data and doesn't credit us? And you can say, yeah, the web is free and we share the information, blah, blah. It's not true. Yeah? When you look at the knowledge bases that are there online, then most of them are under some license that allows you to do everything, whatever you wish, but you have to give credit to the person who created the knowledge base. It has a GNU public license. You can do whatever you wish, but you have to give credit. Now the problem is, how do I prove that somebody took the data from us? Yeah? So we have like Elvis born in USA, yeah, and they have Elvis born in USA. Yeah, yeah. How do I prove that they took it from us? They can just say we typed it manually. Or they can be evil and say, no, you took it from us. Yeah, then we have a real problem. Yeah, so person comes, you took from us. No, I didn't. Yeah, now how do we show? So we have 2 ideas. One is a funny idea, one is a serious idea. Funny idea first. Funny idea is with David Grossamblard from Rennes, is that we add fake facts. This is great fun. So this is a very standard approach, and you might have heard about this from Google. So Google wanted to show that Bing was stealing search results from them. So they introduced a special word that delivered a special result. Yeah? And then when you search for this word, which nobody does, then you go give this special page. And then they searched for this word on Bing. And guess what Bing gave? The very same weird page. And they said, look, you took it from us. And Microsoft said, yeah, no, it's not really. Yeah. So it was a big trouble thing. So this is there. Same idea, add fake information, prove that the fake information comes from you. Maps, same thing. They take a map, they add fake streets and fake places. And whenever this fake place appears somewhere else, they say, you took it from us. This has very funny consequences. So there is a...
You took from them.
Oh, took from them, exactly.
I mean, it's symmetrical.
It's symmetrical. We're going.
You do not reverse. They still claim that you took from them, even you took the fake.
That is totally true. I'm going to come to that. I'm going to come to that one. First, the example with the maps was that there was a map producer who just published a map, and there was the intersection of streets. he said, okay, here in this intersection, we're going to just put an artificial village, Arlington, and put Arlington there just to make sure that this is our data. So then one day came one guy who wanted to open a petrol station at this intersection. So you open the petrol station. How does he call the petrol station? He looks it up on the map. Apparently it's called Arlington, this place. So he calls the petrol station Arlington. Yeah? Then his family comes, moves in, his friends move in, right? And then the other people, there's a small supermarket that opens up, right? How do you call this village? Well, Arlington. Yeah? So now there was fake information, but became real. Yeah? So this is a real problem. So we do the same. We actually built a statistical model of the properties that entities usually have, and we generate fake information from these profiles. So for Elvis, for example, we will not add like he was married to Obama or something, yeah, because like this is improbable. But we will add stuff like he also played piano, which is what many people in his class do. So we actually have this demo, and the demo is that you pick an entity, anyone you like, I don't know, the mayor of Paris or whatever, and we generate fake information, and we show you the entire graph about the mayor, and you have to guess which one is the fake information. And most people can't. Yeah? So we generate very good fake information. We generate so good fake information that sometimes the information is so good fake that it's even true. Yeah? So we generated that Leonardo DiCaprio was born in Los Angeles. So, wow, this is amazing. This sounds so true. Yeah, look it up. It's true. Yeah. So then it doesn't help, of course. Yeah? So you have to generate something that's false. Now, how to guard against this problem that they might say? We use a trapdoor function. There's a cryptographic trick. As a trapdoor function means you have a key, you have a number, say 42. That you choose, yeah? And then comes this function which scrambles it and converts into a different number. Yeah? And the trick is that it's very easy to go this way, but if you have the result, it's very hard to reverse engineer the function, figure out what was the key. Yeah? So we come up with a key, like it usually is a very long number, and then we generate by this trapdoor function the other very long number, and this other very long number tells us which facts to add. How do we do this? We just enumerate all possible facts to add, and we take the one that is given by the number. Now, if we add this information here, and they say, okay, you took it from us, we say, no, because we have the key that generates this fact. And the other ones will say, no, 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 we also have it. Ah, do we have it? Is that right? And they can't produce it, because you can only walk in one direction. The trick. So yeah, don't try it. It's protected. So this is the fun part, and the fun is bad because you actually destroy your own data. Okay, bad. So let's make a serious approach. Serious approach removes information. So we're gonna remove certain facts with the same scheme. And by removing facts, we remain consistent with the open world assumption, because anyway we're incomplete. So we remove just one or two children from Elvis, or we remove the president or whatever, because anyway we don't have them all. We just remove some more. So we have to remove from around like 500 facts. Like if you have several million, you just remove a few hundred. Any small bug in YAGO will remove hundreds anyway. So remove them, and then this gives like a pattern, like the holes in a cheese. Yeah? And when this pattern appears in the other one, you can make a statistical argument and show that this is improbable, that this just arose by chance. Which is very weird. From the fact that you don't have something, I prove that you took it from me. Yeah? This is it took us ages to understand this. Yeah? So I have the details here. It was like Serge who said this. And we said, no, this can't be true. Yes. Yeah?
This still works only provided that the evil guys will store your world data. So imagine, again, Evilpedia of Elvispedia, we store only still the thing of Elvis, and they will. That's totally
true. That is totally true. So we have, like, I will do the details. We can show that. So the trick is you remove some, and then an innocent ontology will overlap roughly in the normal facts and in the fact that you remove. But if you have like Evilpedia, like Deepedia for those who speak German, yeah, Deepedia, yeah, thank you for laughing, yeah. So then you will only overlap in the fact that we don't have it. So there are two tricks. One is you take a subset, as you said, like they steal only a very small thing, and the other one is they steal a small thing, plus they merge with a different knowledge base to cover the holes. Yeah? And so we show with experiments and with statistical arguments that if you remove enough holes, then you can show that the probability that they can do this like decreases below, I don't know, 5% or something. So we give you the formula that says like how many facts you have to remove in order to guarantee with this probability that this is going to work out. But it's a trade-off. If you remove everything, it's the safest. Oh, just kidding. Yeah. Good. Now comes the newest thing, which just got published like 1 week ago. So because people say, hey, you do this stuff there and you protect knowledge bases there, who wants to protect knowledge bases? Do you also protect the user of the knowledge base? do something reasonable in your life, protect people, not knowledge bases. Okay, and here we go. This is the newest thing. And these are two stories which are very interesting and shocked me a lot when I read them. You might know them. So this is Matt Honan, who is a journalist, and this is the hacker whose name we don't know. What happened is, this is a real story, and so we set out to solve the problem. So the hacker figured out that this guy had an account at Amazon. And at Amazon, this was very cool at the time, you could add a credit card just by phoning them and saying, oh, I want to add a new credit card to my account. So this guy added a credit card to the account of this guy. Yeah? Then this guy phoned again Amazon and said, I'm Matt Honan, I forgot my password. And guess what Amazon uses to verify that this guy is really Matt Honan? The last 4 digits of the credit card number. Yeah? And say, I have them. Yeah? Yeah, brilliant, right? Yeah, exactly, brilliant. Right. Once you hit this, then he can access the Amazon account and look at all the other credit card numbers that are really in Amazon. Yeah? From Matt to always. Yeah? And then with the last 4 digits of all the credit cards, he went to Apple, phoned Apple, said, I forgot my password. I forgot Matt's password. Yeah? Okay, give us the last 4 digits of your credit card number, which he just got there. Yeah? So okay, reset the password. Here's the password. Then he went to Gmail, and Gmail actually had as a backup address the Apple ID. So he just said, I forgot my password. Yeah, and then the password went here, and he had the password reset. And once you have Gmail, you have everything, right? Because you just say everywhere, I forgot my password, and then got the Twitter account, whatever. Yeah? So it's a real nightmare. So everything was deleted, and this poor guy made a big article about it. Here's interesting. It's a nightmare. So to protect against this, you have two-factor authentication, which I hope you know and use. Yeah? Do you get a code to your phone? Here's how it works. This was a second story by Owen Williams, also a journalist. And a hacker tried to access his Apple account. But this Owen guy was smart, had two-factor authentication enabled, so the guy couldn't access it. Yes! The problem is that Apple protects the data, and whenever somebody tries with wrong passwords to access it, it blocks the account, and you have to give, like when this guy wants to access it, has to give the recovery codes. Have you ever heard of your recovery codes? Did you print your recovery codes? This guy did not. Which means that he couldn't access it either. Yeah? So all his Apple devices just were locked. Right? Just because somebody tries to break your Apple account, all your devices are just locked. Like your Mac doesn't boot, your iPhone is locked, you have no access to your iCloud, all data is just gone. It's just gone. He phoned everything, it's just gone. It's just not there. Yeah? So this is the opposite problem. So we thought this is a very interesting thing. So we actually model these dependencies. Yeah? And here are the dependencies for your Gmail account, yeah? With two-factor authentication. Actually pretty complicated. So if you want to have access to Gmail, you need the first factor, which is either your password, or if you have like the backup option, you can get it from your Yahoo account. Say you have a backup email address at Yahoo. The second factor can be either a recovery code or authentication by phone, like with this little app, or on a trusted device, you don't have the second factor to log in. So trusted device means like one of your devices, and your phone, you need either the app or the SMS. And for the SMS, you need to possess the phone or have the PIN of the SIM card. So it's a pretty complicated thing. It becomes even more complicated if you have like several dependencies. So like say your Yahoo account also has two-factor authentication, right? It becomes complicated. And so we asked 3 questions. Safety, how many keys can I afford to lose and still have access to my data? So if I lose the recovery key, can I still access my data? Security, how many keys does a hacker need to know to access my data? Just the 4 digits of my credit card number, my password, or does he have to know, have the phone plus this factor plus this? And protection, how many keys are needed to destroy my data? So for example, if somebody steals my phone and my laptop and destroys them, then the data is still in my Dropbox account. I'm fine. Yeah? But if I don't have the Dropbox account and somebody locks this thing and steals this, then I'm just lost. Yeah? Or if somebody steals this, it's not encrypted, he can just delete the data from the laptop, Dropbox will update and empty the Dropbox. Yeah? So it's sufficient that somebody, it's not the case, yeah? I warn you. Okay? If somebody steals this and just logs, it doesn't even have to log in because this is a Microsoft thing. You just take out the hard drive, plug into another machine, Yeah? Then all the locking password doesn't apply. And then you just delete all the files, and then your Dropbox will, by next time you update the other machine, everything's just gone, yeah? Just to scare you. So I said, okay, this is interesting, let's figure this out. And we made a system, Divina, yeah? Discovering vulnerabilities of internet accounts. Yeah? So where it's basically a questionnaire, it's online, I'm gonna give you the URL, where you say, you answer questions like where do you have Dropbox installed, do you have two-factor authentication, and do you have a code on your phone, kind of stuff. And then we compute from this the dependency graph. And we compute like which are the weakest points in this graph, like which are the most important passwords that allow you to access the data, kind of stuff. Right, and then you get for every account, like we do for Dropbox, iCloud, your phone, Dropbox, Gmail, and some others, like maybe the 10 most important providers. Then we compute for you the level of safety, security, and protection. We say, like, look here, this you should enable two-factor authentication or something. I can only encourage you to try it out. It's here. So it just got accepted as a demo at DAP. It's joint work with my postdoc who joined in January, and Ziad from the security group, obviously. Good. We have protected everybody. One short thing about applying these knowledge bases, like there's also a real-world application, and we work with Le Monde. And so instead of extracting information from Le Monde, we actually thought everybody's doing this. Let's do it the other way around. So we actually use YAGO to interpret Le Monde. So we just parse all the articles and build a table like this. You say, like, in this article, we have the timestamp, we figure out where the article plays, and we figure out all entities that are in there. It's very simple, very naive. And then we can make very nice graphs. Here, for example, is the age, or average age of people mentioned, drilled down by their profession. Here, like musicians tend to be younger than politicians, but they also get older. Yeah? Like singers are the youngest, but they also get older. Never older than 27, yeah, but still they get older. So these type of statistics, or like which are the countries that have like most foreign companies. You can do plenty of statistics. It's very interesting. It's all online. It's a workshop paper with Thomas Huet, I think he's from ENS, and Asha from Max Planck, myself, and we have a vision paper because we couldn't get this to work. So if you can't get something to work, at least you make a vision paper. So my wife and I did a vision paper. Good. This is the entire thing. We have seen how to construct them, the knowledge bases, how to mine them, how to align them, how to protect them, how to protect users. Everything was in there. How to apply them to news data. But we have not answered Elvis' question. Yeah. So how come that here says died August in 1977, and we looked it up even in YAGO. Even in YAGO, he says Elvis died. Yeah. And so we say we are very sorry for this. But if you have 100 million facts, and you have an accuracy of 95%, meaning 5% are wrong, that means you have 5 million wrong statements. Yeah? And this may be just one of them. And with this, I would like to thank you for your attention. Are there questions?
So how do you deal with the legal issues with Wikipedia? Because you are having all the information from them.
That's true. That's true. So we use the same license. So Wikipedia is the share-alike attribution license. So we can just take the data and we acknowledge them, like it's written everywhere that we are from them, and then we can just take the data.
So if another database acknowledges you, it will be okay?
Us, yes, but ours is also Creative Commons, meaning that they also have to give credit, but then they can use it, which is what people actually do. And if they don't, we can show that they should. Yeah. Yeah. So, sorry. Go ahead. Go ahead.
Why start mining directly from the data instead of making your engine master first the language, like mining dictionaries or a pure master of the structure of the language before going to the data on the web in order to mine the actual instances from it. So mastering the structure of English, for example, knowing what a singer is a person, is blah blah blah, and afterwards go to the web in order to find singers.
That's a totally valid approach, and this is how we started. Like before YAGO, the work was on understanding natural language, like we did dependency parsing, and finding patterns in language. And the project that I showed to you with Google does the mining actually on natural language. So we find, I didn't show it, but you find phrases that can be mined to map to certain relationships. So we really try to go into the language and figure out not just the entities, but also figure out the meaning of the strings. We do this, yes, we do. I didn't talk about it, but yes, it's a very valid approach.
A question about, so the knowledge base, at which rate does it evolve? So it's continuing going.
Yeah.
Or you do snapshots?
We do snapshots, and the snapshot depends a lot on whether we have PhD students who want to work on this or not. Yeah, so it's a huge effort, this thing, because it looks all the simple, like with a big graph, but it's a lot of engineering also. So we do one update each year or something, and it's a lot of work actually getting these things out.
Can you make it incremental, or is anytime there are so many dependencies that when something changed, it will control the whole graph because you made.
Well, yeah.
You need to reweight all the scaling for the frequency, etc. So
right.
can you do it incrementally, or really
we could. So the entire process, these things they originally ran like in 4 days, and then we bought a new machine and it runs in 10 hours. So this is great, right? So you just buy a new machine, and if it runs 10 hours, then in theory, we could download Wikipedia every 10 hours and run it. Now, if you want to go, we could subscribe to the RSS feed of Wikipedia, and whenever a new fact arrives, we just put it in there, and then do incremental thing, and then it would be very interesting to see how it back propagates and forward propagates, what are the influence, whatever. But given that it runs in just 10 hours, we did not venture in this direction. DBpedia does. DBpedia has DBpedia Live project, which listens to the RSS feed and integrates the data. Although they say it's a lot of engineering as well, so it's not easy actually. Yeah?
In line with what Dario just asked, why didn't you consider to transform your YAGO into a wiki YAGO, like putting it there and having people updating information?
Totally, absolutely. So there are two projects that go in this direction. One is Freebase, one is Wikidata, and they're going to merge because Freebase was bought by Google, and the boss of Wikidata was also bought by Google, so then I put it together. So, and there people do this manually, that is, they manually enter information. And we, in the beginning, we collaborated with Freebase. We gave them our code, so they could bootstrap their data set with our code and then do it manually. And now we contacted Wikidata and we said, look, I mean, instead of starting from scratch with your stuff, you could start with what we have already. The quality is pretty decent. It's easier to correct information than to come up with it from scratch. But they said they are purists and they want to really start from scratch and not have any automation in there. They might change their point of view, but this, when we contacted them maybe 1 or 2 years ago, when they said they did not want it.
But is it not, should it not be the tendency that instead of writing text in Wikipedia, write it in a structured manner so that it becomes richer and more gives access to information in a more intelligent fashion?
This is exactly what the Wikidata project thinks too. So they want to bootstrap everything just manually, and you have like drop-down menus for the relationships. You just enter triples. But they didn't want to, I mean, maybe they change opinion by now, I don't know, but at the time they did not want to. They are purists.
You work basically with text. Do you think it would be useful to include other types of media like images or videos or?
That would be fantastic. Totally. So
I don't know today if it would be possible, but in the future I could think of.
Totally. I mean, Google is doing a lot of progress on this. So we had a talk recently, and they say that they can figure out when in the video what happens, and then, so they are very, like when you search for a cooking recipe, how to like fry an egg, they will scroll in the cooking video to the exact second where they start frying the egg. So it's pretty amazing. There is a project at Max Planck that goes in this direction. I try to mine common sense knowledge from videos by help of the subtitles. Right, so like Mary enters the kitchen, right, and then you see Mary enters the kitchen, right, and they try to mine this kind of information. We don't have this at Télécom ParisTech right now with YAGO. We don't have this right now, but it's a very interesting direction, totally.
And what is the status of this project compared to existing applications like Wolfram Alpha? because I know that they pretend to be a knowledge engine, and I know the guy is very cocky, but it looks very powerful. They're a very great result. How is the project compared to that one?
So there are several projects. So one is the Wolfram Alpha. The other one is IBM Watson. You might have heard of this. And I mean, Google itself, right, with the knowledge cards and everything, is going the same direction. So everybody's going this direction. And so the way that I think I should position myself, and we have been positioning ourselves, is that we are scientists. So what we do is we open doors. So this YAGO thing, this started like 2007. So where nobody thought of this at all. Like Google didn't think of this at all, and Bing didn't even yet exist. And so we opened this door, and then we built YAGO, and now like 5 years later they do it, and they do it much better than us. And now we open other doors. We do knowledge mining, which they can't do, and they will do one day, and they will do much better than us. Now we do multilingual stuff, which they can't do, and one day they will be much better than us. So I see myself or our research as always opening doors and then letting others perfectionate it. In the same way as Wolfram Alpha, which is fantastic and everything, but they have much more manpower. Like we have like 12 people who work part-time on this, and they have programmers or whatever, right? They had their own programming language. So there are some successes. So for example, the IBM Watson thing uses YAGO. They just import the data. So these are like the things that we are proud of then. Yeah.
Question about the controversial part about protecting knowledge bases, which is, I mean, if I would select a subject which is like, what is the wrong element in the picture is that. So, I mean, it's more a security subject. Then, okay, you have a graph, you use part of the same method, but what happens if there is something you don't consider? Like the fact that Amazon allows anybody to take a phone and do stupid thing to pollute. So to I mean, I'm not sure that your knowledge base, your dependency graph, encodes really all the possibilities. If you didn't consider that,
oh, you mean
the phone in.
You mean this? I see. This thing, right? This thing. Yeah. Totally. Yes. So this is. We have a disclaimer. Everything we say, like, we can't guarantee. So we model this graph based on, like, here are the sources based on their description of stuff. So they say, like we tried out yesterday, say, I forgot my password, and we see what options we have. But if there is an option that we don't know about, for example, your phone, and even though it's written nowhere, if I do give you the 4 credit card numbers, 4 digits of my credit card, they will still reset the account, then we don't model that, that's right. So there's always one degree of uncertainty. Yeah.
I mean, it's very interesting, but my question was, why didn't you work with some guy in the security teams?
There, right?
Huh?
Yeah, I would love to, totally.
Or, I mean, also I mean, you are more knowledge-based guys.
Yes.
Still. So KB for me, it's a kilobyte.
Okay.
It's a acknowledge-based, but still, I mean, here is some guy for which KB has some meaning, is more security, I guess.
Yeah, totally.
Very...
So this guy is from is in security group of, and we go together to lunch, and then he told me what of his problems. I said, okay, good, we have to find a solution. Yeah, but it's true. It's just a first step. So I find it's extremely exciting, and if we could do more here, it would be amazing. Totally. Yeah. Yeah, please note down the URL. Yeah, please. Yeah. Thank you. Hey, ça va et toi?